Hello and welcome to my YouTube channel. In today's video I'm going to be talking about the Pythagorean Theorem. In particular, I'm going to step you through a proof that is attributed to Albert Einstein. In my opinion, this proof helps show very clearly the reason why the Pythagorean Theorem is true. So, of course, you know the Pythagorean Theorem for a right triangle with legs a and b and hypotenuse c very simply states that a squared plus b squared equals c squared. And we're going to look at this triangle and we're going to prove this truth for this particular triangle. This triangle has two angles here. We'll mark that with one arc, and we'll mark this with two arcs, the one that's a little bit smaller. And Einstein's proof basically goes like this. You take a line from the right angle and you drop a perpendicular to the hypotenuse. And because it's a perpendicular, this angle has to be 90 degrees and this angle has to be 90 degrees. Now what I want you to notice is that because this angle and this angle must sum to 90 degrees, this angle and this angle also must sum to 90 degrees. In fact, we'll soon show that this angle here is equal to this angle, and this angle here is equal to this angle. So what I want to do is I want to switch colors, and because we've divided it into two triangles, I'm going to color this one red, like that, just to make it clear, and then I'm going to flip it, turn it, and copy it down here. So we're just going to draw it up like that, and then we're going to draw it down like that, and then the base like this. Okay, the first thing, of course, this triangle has a right angle here, and that right angle landed here. The second thing I want you to notice is that with the larger yellow triangle, this angle is coincident with the red and the yellow triangle, and that angle is right here. And because these two angles are equal for the red and yellow triangle, that means that all angles have to sum to 180, therefore this angle must equal this angle. So the red triangle is similar to the yellow triangle. Similarly, we're going to go ahead and mark this one as blue. So we're just going to trace that out like that. Trace that down like that. And we're just going to highlight that. And what we're going to show is the same thing is true for the blue triangle. So we're going to draw that one here. It's a little bit bigger. And we're going to draw it down like that. And of course it has a right angle here. And that right angle landed here. With the yellow triangle, this angle is coincident with the blue triangle, so that angle landed here. And of course, because with the yellow triangle, two angles are equal, the third angle must be equal. And then finally, we're going to draw the original yellow triangle here, and just down like that. And we've already established that this angle's like that angle's like that, and that angle's like that. Because all three of these triangles have the same shape, meaning their angles are the same, they are similar triangles. Furthermore, what I want to point out is that the actual hypotenuse of each of these triangles, this hypotenuse came from over here, and we're just going to write that as a red A. So the hypotenuse is the leg length of the yellow triangle, but it's the hypotenuse of the red triangle. Likewise for the blue triangle, the hypotenuse here, we'll color that B, and we're going to put that down here. And then also, of course, for the yellow triangle, we have C. Now what I want to do is I want to write the area of each of these triangles, and of course it's very obvious that the area of the red plus the area of the blue is equal to the area of the yellow. So I'm going to write the areas as capital A, capital B, and capital C. And of course that translates to A down here, translates to B down here, and it translates to C down here. And of course we just established that because the red and the blue came from the yellow, A as an area, B as an area, added together must equal to the area C. Okay, now we're going to take a little bit of an aside, and we're going to talk about similar triangles. So let me just partition our drawing here, and let me draw. And this will be true for any triangle, and we're just going to draw that like that. And it almost looks like an isosceles triangle. Didn't intend to do that. We'll call that the base. We'll call this the height. And the area of this triangle, we'll just draw that as capital A, and we'll give it a little subscript of a triangle so it's not to be confused with the A over here or the A over here. And we're going to say the area of that, of course, is 1/2 base times height. And then what we're going to do is we're going to draw a similar triangle to that. And we're going to stretch the base a little bit by a factor, and we're going to stretch it by a factor alpha. So the base is going to become alpha b, and for it to be similar, the height also has to stretch by that same scale. And there we have the height stretched as well, and the height now becomes alpha h. And then we're going to compute the area of this triangle, and we're going to call it a subscript triangle, and then we're going to give it a prime just to represent that it was scaled. And of course the area is 1/2 the base, which is now alpha b, and then the height, which is alpha h. We're going to recombine terms here, and we're going to pull the two alphas out, so there are two alphas there, so we have alpha squared. And then the rest of the terms we're going to put in parentheses, so we still have a 1/2 there, we still have a base, and we still have a height. Now the thing I want you to notice is that this quantity here is equal to this quantity here. So we can use this symbol as a substitute, and we can write that as alpha squared times a subscript triangle. And the thing that I want you to notice is that we are representing the area of the larger triangle in terms of the area of the smaller triangle. In other words, the smaller triangle is our unit of area. So we're expressing the area of the larger triangle in terms of the area of the smaller triangle. In other words, our units are whatever this area happens to be. Not square meters, not square centimeters, but a sub triangle. That's our unit. So our area scales as alpha squared. Again, linearly, the lengths scale with alpha, but the area scales with alpha squared. So what we're going to do is we're going to make a triangle that is likewise similar to our three triangles over there, our red, blue, and yellow triangles. And we'll mark that as the right angle, and then this is our larger angle, this is our smaller angle. And what we're going to do is we're going to choose the hypotenuse to be equal to 1. And the reason why we're going to do that is because we notice that this side here scales as c times 1, this side scales as b times 1, this side scales as a times 1. And for these triangles, the scale factor from here to here is a, from here to here is b, and from here to here is c. So if they scale linearly with a, b, and c respectively, then their areas must scale with the square of those numbers. So what we're going to do is we're going to notate that this area is u. Again, that's our unit of area, and I'll leave it to you as an exercise at home to verify that u is equal to ab over c, where a and b and c come from the edges of this original triangle here. So then what we can do is we can express the area, capital A, in terms of this unit. So we're going to, and because it's a times 1, the scaling factor for area is going to be a squared times our unit of area. And then for the blue triangle, it's going to be b squared times our unit of area. And then for the yellow triangle, it's going to be c squared times our unit of area. And of course we have, this is equal to, this is plus, this is equals, so we have a squared u plus b squared u equals c squared u. And because u is not equal to 0, we can cancel it out, and we're going to go ahead and do that. Cancel, cancel, cancel. And what we're left with is the familiar a squared, and then we have b squared, and then we have c squared, and plus, and equals. And that is the Pythagorean theorem. And the reason why the Pythagorean theorem is true is because you can take a triangle with a right angle and you can divide it into two similar triangles. The key thing is that this is only possible when you have a right triangle. You can try it with an obtuse triangle, you can try it with an acute triangle, it won't work. Only a right triangle can you divide the triangle into two similar triangles, because these two angles are equal to 90. These two angles are likewise equal to 90, and in fact they're equal. And then that creates three similar triangles which are scaled by A, B, and C respectively. And that means their areas are scaled by a squared, b squared, and c squared, and that is why the Pythagorean theorem is true. Thank you very much.